Good morning, and you're welcome this morning to the 26th in the series, in the Signpost Series. My name is Pat Murphy, and I'm Head of Environment Knowledge Transfer with Teagasc. The Signpost webinar series is brought to you in collaboration with National Rural Network, Dairy Sustainability Ireland, and Food Drink Ireland SkillNet. You can send us your questions by clicking on the Q&A tab at the bottom of the screen. And today's presentation, along with the recording of the webinar, will be made available on the Teagasc website in the coming days. Today, we're very happy to be joined by Per-Erik Mellander, catchment scientist at Teagasc Johnstown Castle. Morning, Per-Erik. You can turn on or unmute your sound there. Good morning.
Good morning, Pat.
Per-Erik, you're an almost naturalized Irishman at this stage, hailing from Sweden.
That's correct. I've been here for 12 years now.
Okay, so you're around. The Catchments Programme is 12 years old at this stage, so you're around right from the beginning of that programme.
Yes, yeah, I came over here to work with the Catchments Programme.
Okay, and your talk today is on findings from 11 years of high temporal resolution monitoring in the Agricultural Catchments Programme. So without further ado, I'll let you get started. Again, remind people, I suspect there'll be plenty of questions in relation to what we're looking at here. So if you want to share your screen, and we'll proceed to the presentation. Thanks, Per-Erik.
Yeah. Okay, so in this presentation, I'm going to give an overview of the Agricultural Catchments Programme and some general findings and aims for the future. So the Agricultural Catchments Programme have been monitoring water quality in the river outlets of 6 catchments every 10 minutes for 11 years. So there's no way that I can sum up these 11 years now of this big program in 25 minutes and do justice to the program, but I will give an overview of my conceptual understanding that's been built up over the years together with the team. So the drivers behind the programs are, of course, agriculture, environment, and policy. And as an EU member state, we are under the Nitrates Directive required to assess the National Action Programme. And we have here in Ireland the Good Agricultural Practice, which has been in legislation since 2006. And this includes baseline nutrient mitigation measures. And that's where the Catchments Programme come in. We were implemented in 2008 by Teagasc to monitor the efficacy of the measures of the Good Agricultural Practice. And then later in 2014, we had the Water Framework Directives. There was an implementation group that was started in the EPA to attain and sustain at least good water status. And then we have Food Harvest 2020 and Food Wise 2025, which are about increasing the knowledge, scientific evidence, and value of the primary output. And also then on top of that, we have climate. We have a challenging climate in Ireland and also a changing climate. In the last decades, we experienced more rainfall than the most rainfall in over 300 years. And in 2019, Ireland actually declared climate emergency. So on one side, we have food production and climate change. And this we need to keep a balance then with good science and environmental policy. And I hope that's where we might see the Agricultural Catchments Programme also fits in. So the program started in 2008. It's ongoing, and we are on our 4th cycle of funding from the Department of Agriculture, Food and the Marine. And it's a collaboration with over 300 farmers across 6 catchments. And we're a big team. I don't know exactly how many we are at now, but we're more than 20. It's a team consisting of scientists, advisors, technologists, and technicians. And we use a whole catchment approach. And as a conceptual framework, we use what we call the nutrient transfer continuum. So that is a kind of a framework that makes it easy for us to use the same approach across all the catchments. So we follow nutrients from the source, how they may be mobilized and transferred via different pathways. And along those pathways, there might be transformation processes and delivery to water where there might be an impact. And we have the same experimental design across all catchments. And I think that's one of the strengths with the program as well. And that experimental design also follows very much this nutrient transfer continuum. So for the sources, for example, and mobilization, we get a lot of information, of course, with the farmers on the ground there via our advisors. Also, all the fields are sampled on the field by field basis. And this is done in the start of each funding cycle. So we're just about to do our fourth survey across all the catchments. For the transfer, we of course need to understand the weather. So we have in each catchment, we have a weather station in the center of the catchment. That's a full station with the rainfall and all the parameters that can be used to also estimate the evapotranspiration. So we know the water that's coming into the catchment and what's going back to the atmosphere. And transfer can of course be by different pathways. So just as an illustration here, for surface pathways, we have a detailed survey of the landscape and built a digital elevation model. So we have a very good topographical map, very detailed, and we can combine that with lots of other information and find out areas where most of the surface pathways are. And of course, then combine that with the weather, we will know more about the timing of these. There are other ways, indirect ways, that I might mention as well later. But there are also below ground pathways. And for these, we need to look into the ground, of course, and we have multi-level monitoring wells. We have a few monitoring wells around the landscape. Most of them are in transects, hill slopes. And these typically screen different depths, so in the subsoil and in the weathered bedrock zone and deeper bedrock. And we're there monitoring the water table flux, how it changes, and we can get an idea of which directions water is moving, vertically and laterally. But the good thing is we can also sample these, and we do so every month. So we sample all of them for a chemical analysis of nutrients and metals. Then for the delivery, we have in each river catchment outlet in river, we have what we call an outdoor lab. So first of all, we have also a where we can monitor how much water is leaving the catchment in the river. So combining that with the information we get from the weather station, we get a full water balance, a water budget. So we know how much water is going out there, and in that water in the river, we also have sensors, optical sensors, and one of them reads nitrate N concentration. Another one is also for total organic carbon. And we have for turbidity, that's how it's a proxy used for how much sediments it's in there. Electrical conductivity and temperature are also there. But then we have actually also a sample automatically been taken every 10 minutes for analysis of total phosphorus and the total reactive phosphorus concentration. So we have all of these parameters collected every 10 minutes in all of the rivers in the catchments. And there's also a sample being collected at multiple places along the river network. I think it's up to 10 in each catchment, also for chemical analysis on a monthly basis. So for that, then we get more of information across the whole river network. And finally, for the impact, we have a group from UCC who makes ecological survey. This is done twice per year in May and September, and they analyze for diatoms and macroinvertebrates. And you may ask why so much data, and first of all, maybe how does this data look like even? This is a graph of 10-minute samples of reactive phosphorus over 11 years. And it's immense. I think this is about 500,000 data points in this graph. And it may seem like overkill, but there's a lot of information, very useful information coming out from this. And I just list a few of them here. First of all, it captures all. We're not missing anything, and we're not risking averages being skewed by some data points. So we believe we get a good value of good information in this. It also provides insights to water quality during different hydrological conditions, so during low flow and high flow across the year. And we can detect even subtle changes in water quality. And by being able to create, for example, annual averages that we know consists of a full time series, we can use that to link to larger scale weather systems and link that to water quality and understand the effect of what's causing what. So if it's mostly a weather driver behind or not. And then it can be used, we have been developing new ways of identifying and quantifying pathways of nutrients by this. So we can separate quick flow pathways and below ground pathways and interflow pathways with this method. And of course, we can use it to validate and even build models and test other sampling schemes. Maybe in some areas you don't need so much information, and this can guide you to the frequency that would be required for that system. And it can be used also to interpret the frequency of the low frequency sampling, what that actually means. If you have a time series that's maybe only sampled a few times per year, you can compare it to this and with other parameters too, and get a lot of information also from that data. And of course, then having these very data-rich areas to build knowledge from that and extrapolate that knowledge to other areas, larger areas. It's also been used quite frequently as an educational platform, and I find that very, very good. So Ireland has a very diverse landscape, as you all know, and it has many soil types, landscape features, and a complex geology, and also different types of land use. And all these things that affects the nutrient transfer pathways and transfer times and transformation processes then varies highly within a catchment, but also between the different catchments. And that's very important to recognize when look at these different catchments. These are the 6 catchments we've been working with. They're spread across Ireland, and they're all chosen to represent intensively managed land in Ireland, but all on different physical settings. So typically chosen to represent different riskiness in terms of phosphorus loss or nitrate loss. And that's very much to do with the soil drainage. So some catchments with very heavy soils were believed then they would have a lot of surface pathways and that will carry phosphorus, while well-drained soils will leach nitrates. And in many cases, that was true, and our first initial assessment of the riskiness was confirmed. In other cases, it wasn't true, and we just realized that the picture is so much more complex. So we really have to understand how the physical settings is and chemical settings together with agronomy is affecting nutrient loss. So here I have framed 3 of the catchments. It's the Layer Catchment, Continuum Catchment, and Timolene. And those 3 catchments, they all have high concentrations of phosphorus in the rivers, above the levels where they should be. So they're all elevated, but for 3 very different reasons. And what I'm going to do now is I'm going to go through each of these catchments and give an example of why they are high in phosphorus concentration. Start off with the Layer Catchment. It's all about here agronomical controls. So it's an arable land on poorly to freely drained soils, and there are complex pathways in this catchment. And the phosphorus concentration has proved to be high in all of these pathways. And that's a lot to do with what we found also from our soil survey, because there actually was an increase in index 4 soils here in this catchment. So this is then what we would call a source risky catchment. It's good farm scale nutrient management would be needed to improve the spatial distribution of nutrients here, and there's plenty of room for improvement. So have this in mind. This is a source risky catchment, and here is another type of risky catchment. It's a Timolene catchment in West Cork, where it's much to do with the chemical controls. This is a grassland on freely drained soils and also very iron-rich soils. And iron-rich soils favored phosphorus into soluble form, which is then leached into groundwater. So when comparing this catchment with another free draining catchment, which was aluminium rich, we found that 50% of the phosphorus was lost via below ground pathways in both of the catchments. So below ground pathways were very important in these free draining catchments, but excuse me, the loss was 3 times higher in the iron rich catchment due to the more being in a more soluble form. So this was a mobilization risky catchment. It's also important, though, to have in mind that this catchment has very high source pressure, so there will also be source issues. But to conceptually understand what we've been looking here, it's about mobilization riskiness, and phosphorus leaching can be important also at the whole catchment scale. But there are also likely to be hotspots for leaching of phosphorus in these catchments. And we would like to find out more about that. And we have a student project that's looking into it. And then finally, the third catchment typology, the Ballacanoe catchment in Wexford. It's a grassland on poorly drained soils. So it's very heavy clay soils and hydrologically flashy. That means it responds quickly to rainfall. And it will be dominated by quick surface pathways. And when comparing this catchment with its neighboring Agricultural Catchment, which has freely drained soils, we found that for the same river flow, this catchment had 3 times higher phosphorus loss. And it wasn't to do with the sources, because they had similar sources in the soils. So this is an example of a transfer risky catchment where hydrology overrides the source pressure. And I think it's quite clear that all these 3 catchments, despite having phosphorus risk, it's clear that there is for 3 very different reasons. And there's no one-size-fits-all solution to this. We need to understand how the catchments behave and respond to nutrient loadings and response to weather conditions and which type of pathways are involved. But I also like to give this example that there's not only a steady state situation between the different catchments, there's also temporal variability. And this is an example from Agricultural Catchment with well-drained soils, where normally the pathways would be dominated by below ground pathways. It would be a groundwater driven catchment. Here looking at a summer rain event compared with a winter rain event. The summer rain event had a soil moisture deficit of 31 millimeters. And in the winter event, it was a soil moisture deficit of 0 millimeters. And what that means is that if you see the soil as a bucket, 31 millimeter soil moisture deficit means that there's still room for another 31 millimeters before the bucket is full. And that's, of course, when the soils are dry in summer, the situation. But in winter, the soils are moist all the time, and there's little evapotranspiration. So the bucket was already full. It was all 0 millimeters left. So I guess you can understand what happens then if you have a rainfall event. This summer rain event, this is real data. So this was 25 millimeters, and the winter rain event was almost the same. So 4 millimeters more, 29 millimeters, but in the same magnitude. So what happened here is, if you look at the river flow, what's coming out on the other end, it was only 2 millimeters in the summer event and 20 millimeters in the rain event, in the winter event, despite being more or less the same magnitude. So 10 times more flow in the winter event, and that of course influences the phosphorus loss. In the summer event, it lost 1.6 grams of reactive phosphorus per hectare, and in the winter event, 6.5 grams. So that was actually 4 times higher phosphorus loss in the winter event in the same catchment. So the timing, the antecedent conditions are very important too. And this is one of the reasons why there is a close period for spreading. Now, this is an example of our critical source area maps that was developed by Ian Thomas. This is actually putting the information I just been giving here now. This is more or less a composition of all that in different layers. So this is first of all built on a LiDAR map image, a digital elevation model with high resolution topographical information, and then superimposed information on the soil phosphorus concentration, erosion risk, mobilization potential, and areas, hydrological sensitive areas. And by doing so, we can identify the critical source area, the risky areas for nutrient loss. And those are the red areas in this image. If you zoom up, you can see then that will be surface-driven pathways there with delivery points. And of course, this is a way to go if you want to have a very targeted and efficient measures. Instead of, for example, having a buffer strip along the whole river network, you could target these delivery points. And then, of course, we have the weather. That's quite challenging. And I would just like to review. I know you have it all very clear in your memory, all the different types of weather we had recently. But as an example, from the hydrological year of 2018, and hydrological year starts in October. So I'm just going to show here from October 17. It started off with Hurricane Ophelia, which was quite a severe event. It was more associated with winds and possibly didn't have that much influence on water quality, but it was a significant event. And it was followed by winter, and as it says here, the wettest in over 300 years. And then we had this situation when the beast from the east, the cold air from the east, met up with tropical storm Emma and created this massive snow event. Here, my kid standing on what is the road to my house. It's a lot of snow. And this was then followed by a severe drought in summer of 18. And then this is just almost normality now for this time of the year. We all remember now, even last weekend, Storm Alex. This is not Storm Alex, but it's just an example of these storms that we're getting more frequent coming into Ireland now. So climate change is one thing, but there's also a natural system, and they're of course interacting with each other, but I think we can see them as superimposed in each other. We have the North Atlantic Oscillation, which is a big weather system, naturally occurring, and being an island in the Atlantic, of course, we are very affected by this. And this composes by a low pressure cells over Iceland and high pressure cells over the Azores. And it funnels in, sometimes it gets more intensified and funnels in a lot of wet, moist areas, air, and we get a lot of rainfall in winter. And it also creates more drier summers. So this situation with more intensified pressure cells is occurring more frequently now, and it can be expressed with an index. So it's nothing new, it's been monitored for a long time. Here's a time series from the 1950s up to now. And what this clearly shows is that during the programs, the period that we've been monitoring water quality in the Catchments program, we had a sharp increase in this index. And it has affected what we're looking at. Nitrate and phosphorus concentrations were correlated to changes in this index. But there were different responses for different catchment typologies, these different types that I showed you before. But weather changes may override local management is one of the outcomes. So this is not an excuse for anything. This is just to illustrate that the weather influences what we're seeing as well, and we need to know what is causing what. So we draw the right conclusions, and particularly for choosing mitigation options. And of course, in climate change lies also a lot of weather extremes. So these are events that may drastically offset the normal conditions, the baseline conditions. And it may also alter the type of riskiness and require additional mitigation strategy. And I'm just going to give some example of that from our catchments. We have, for example, again, I'm going back to Ballycanoe catchments, which is a long-term phosphorus transfer risky catchment with mostly grassland. And you can see this is just a photo from 2018, summer of 2018, where the grass was very, very dry. And there was poor growth, so it didn't take up much nitrogen. And this started then to build up a pool of nitrogen in the soil. And then due to the warmth and the drought itself, was a lot of mineralized N in the soil, building up the pool even more. And potentially also being a clay soil, when it dries up very much, there will be soil cracking. And then after summer, when the rain comes, there's a lot available nitrogen in the soil to be flushed out and via preferential flow paths and into the river. And that's what happened. What you can see here is a graph of the nitrate N mass load in kilos nitrate per month, plotted against the river flow in this chart in millimeters per month. And you can see there's a clear linear correlation in this, but there's an offset. This red circle there, that's November month. And that was the the first month when after the drought, where you start having a lot of rain, and it actually offset the nutrient loading with 54% of annual average in that month due to this drought. So, So this long-term phosphorus transfer risky catchment temporarily became nitrate risky in this situation. And then we go to the neighboring catchment, Agricultural Catchment, which is long-term nitrogen risky catchment normally. But in this case, the photo here, what you see is actually surface runoff. Despite having these well-drained soils, this is an example of the winter condition I showed you before. The soils were saturated, and there was a massive big rain event in, this is from November 2014, and which created a lot of surface runoff here. And if you look here, this is a time series of the total phosphorus loads, mass loads. So kilo total phosphorus per day and hectare as a time series. And you see this big spike in the middle. That's this event you see on the photo. It's 13th to 14th of November 14. And it was 106% of the annual average phosphorus loss in only these 2 days. So this long-term nitrogen transfer risky catchment became temporarily phosphorus transfer risky due to these extreme events. So what I want to say here is that the influence of long-term weather shifts and short-term weather extremes both need consideration and require different mitigation strategies. And finally, another effect of the summer drought is the effect of a small point source. Even a small trickle like this, it's actually here it's time series in summer of 2018 again, when it's time series of reactive phosphorus concentration, milligrams per liter. And what you can see here with this high temporal resolution 10-minute monitoring, that you have 2 spikes at 10 o'clock and 7 o'clock, 10 o'clock morning and 7 o'clock evening every day. And it was corresponding directly to the milking and washing of the platform. And only a small trickle from this has an influence in the river, because the river is so low at that time due to the drought. So there's no dilution of this. So it elevates the concentration very much. And this increased impact of point sources, in this case, increased the concentrations up to 2 milligrams of phosphorus per liter. And that's way above the standards of 0.035 milligrams per liter. So even a small source may significantly elevate the phosphorus concentration. And this is during a time that's ecological sensitive. So with this, I just want to take us to where we're going in this current phase, the 4th phase of funding on the program. We have an increased budget of 65%. And we're then going to extend our data collection and have new research associated to this. One thing we're, for example, looking into pesticides, and we're looking into other compounds as well. Farm scale monitoring on nitrogen and phosphorus solution, and the groundwater on derogation and non-derogation farms. And we'll also have towers for monitoring of greenhouse gas emissions. And test above baseline mitigation measures. So being able to test directly the efficacy of some measures. And model scenarios of intensification, both of farming and weather, and upscale to regional and national scale. And then just finally to summarize this, efficient and targeted measures are needed. So continuous monitoring has provided us with an understanding of why, where, and how nutrients are lost to water. And there's no one-size-fits-all solution due to the different catchment typologies. And there are also different dominating pressures in these different typologies. So some might be more dominated by source pressures, and some dominated by mobilization, and others by transport. And there's also an overriding climate pressure, long-term changes and short-term extremes. So with that, I would like to thank you.
Thank you very much, Per-Erik. If you could just stop sharing there.
Yeah. Oops.
Apologies to Per-Erik. I forgot to introduce him at the beginning of the talk. We're also joined this morning to assist in questions by my colleague Per-Erik Foley in Teagasc Johnstown Castle. Okay, we have I suppose a really interesting presentation, Per-Erik. The one thing that comes across to me is there's a lot of data there. There's a lot of work in terms of interpretation of it. A lot of learning, and I suppose what you've been able to do in half an hour really doesn't do it complete justice.
No.
Per-Erik, you might just have you any questions coming through there?
We've lots of questions coming through, Pat. I suppose the first one, I get one of the hardest ones out of the way, and I know we kind of want to avoid any political statements or what have you, but there's a question here, Per-Erik. You've showed a couple of pictures of dairy cows walking down the roadways, and you kind of highlighted the impact on the catchment that they're in down in Cork. And there's one question here: is the current demonisation of dairy farming for its effect on water quality justified? So I suppose, what is the impact of dairy farming on, or what are you seeing?
Sorry. Could you just repeat?
So I suppose, Per-Erik, you showed a number of images of dairy cows in your slides, and there's a question here around the impact of dairy farming on the catchments, and what are you seeing from dairy farming, and I suppose what's showing up in your results?
Yeah. Okay. So again, I then had to go to the complexity of the catchments, because there is no directly link between the source pressure and what's coming out in what's actually leaving the rooting zone and coming out in the water in the rivers. In some catchment there might be more of a direct link, and others there's not. So it depends very much on the soil types and the different pathways associated to it, and the attenuation processes along those pathways. So actually what I'm saying here, there's no direct quick answer to that. Some catchments we see an increase in concentration with the intensification, and others we don't.
Okay, can you determine if the P in transit is natural, is of natural form, or is from a chemical fertilizer being applied?
If we have any methods, you mean to distinguish?
Yes. Yeah.
There is actually a Walsh Fellowship, a student project that's working on exactly this. So with other words, we cannot do it now, but we will be able to do it.
Okay, so the plan is to be able to.
Yes.
Great.
Yeah.
Well, a similar type question then, and maybe it's the same answer, but in the example that you gave there in Castle Dockrell, so you had your 31 millimeters, you gave the example of the two buckets, and the P loss that was overland flow. Could you kind of determine whether it was overland flow or was most of it lost through the soil?
Okay, yes, we can determine that. We have methods using all the information, the monitoring of the hydrology, the discharge, and we can do what we call a hydrograph separation, but we can also do that with the concentration and the mass loads. So we can separate the pathways, and we can see, for example, in a winter event like that, it was absolutely dominated by surface pathways then. So in that big event that I showed an example of an extreme, that was near 100% of the phosphorus loss there. And we can also see the effect of that indirectly, since we monitor different fractions, different species. So we have total phosphorus and reactive phosphorus, and the difference there would be particulate or organic phosphorus. And that difference then increased drastically, which indicates a lot more particulate phosphorus, typically for surface pathways. So we can get it confirmed in many ways. There is a change of pathways over the years, over the year, and in wintertime there would be more surface pathway.
Okay, if you were let's say dictator over that region, what would you have the farmers do to make sure that they kind of avoid the losses that you're seeing on those soil types?
Okay, so those maps that I showed you of critical source areas, I think they will become very important because some areas contribute more than others. So what I would say is avoid critical areas and critical times would be.
Per-Erik, there's just, I suppose, a couple of things there, just what might bring people's attention to. There's a question, there was a question there about further information, and there are a number of reports of each of the catchment. There's a report from each of the iterations of the catchment, and there's also, you've had a number of conferences. So just to say to people that we will and can put up our email to the audience, links to some of those after the conference today. So we will put it up on our website and email it to you if that's okay. The question there in relation to drought, is there an argument for catchment-based drought management plans to control nutrient losses?
And just to add to that, Pat, there's a similar one, Per-Erik, there on the same tone. Do we need to improve our management of spreading fertilizer during drought situations, referring to the soil moisture deficit?
Absolutely, absolutely. I think that would be very useful. But I think this is where good, accurate weather forecasts will be very important in this planning. But I think this is very important to get through.
Okay, how can local community-based catchment projects engage more with Teagasc locally? So I suppose, is there more ways to reach out to you guys and get more involved?
Yeah, well, first of all, they're very welcome to contact us, and we do have a lot of visitors out in the catchments and a lot of engagement, and I would encourage more of that.
Per-Erik, a question there. Are there plans to increase the number of monitoring stations to other catchments? And I suppose a topic that you said at the beginning, you're focusing on intensively farmed areas. But yet, when we look at the water quality data from EPA, we see that an awful lot of the lower quality waters are in actually non-intensively farmed areas. So I suppose the question is there any possibility or plans to extend monitoring?
Well, at this stage, it's not a plan to extend with more areas, even though I think that would be a good idea. I think what the plan is to extend our monitoring within our catchments as it is today. But we would use this detailed information we're gaining from these areas and scale up to other areas where you have less information, and to areas, maybe less intense areas as well. And you use our model studies as well, using these areas to build our models and extrapolate to these areas. And there is a lot of good data existing from the EPA on a national level that we could use for this to link.
Okay, Per-Erik, we have a question here just around buffer zones. We've talked about the overland flow and loss through the soil. How effective are the buffer strips that we've had other speakers speak about previously on our Friday morning?
Well, it's again, I refer to the type of the typology of the catchments, I mean, in some areas they would be very effective if you know if they can be targeted. And we heard Daryl Hulakan speak about the smarter buffers. I think that's they need to be the smarter buffers. We need to know what type of buffers to the right measure in the right place.
Okay, so that question kind of keeps coming up again, Per-Erik. We have another one here again. Some of the impacts highlighted appear to be related to climate events, obviously climate change. So how realistic is it to expect farmers to mitigate for these, and what practically can they do? And I know you mentioned that it's going to take really solid weather forecasting, but you know, if you were to advise the farmers, or what do you see farmers in the catchment areas? Obviously, they're getting more intensive advice because they're working with you guys. So what changes are they making on their farms?
Yeah, well, first of all, to go back to that, what they can do, the measures with the buffers, for example, I showed that example where there was a catchment which is actually dominated by below ground pathways, where you may think then a buffer, something in the landscape there mightn't do very much good because most of it is bypassing below. But then you had that event when 106% of the phosphorus was lost over 2 days. So even if it's only a very temporary event, it might be worth mitigating that with also something on the surface. And it's all about then targeting, knowing where these delivery points are and finding out. So but by finding these delivery points is one way, and I think there are loads of other ways a farmer can do to mitigate. I mean, we already mentioned to know when and where nutrients are mostly lost and avoid these areas and times. Other maybe easy gains, low-hanging fruits, so to say, is to identify maybe these drains, manage drains better would be a good thing. So this point source that I showed you an example from would be an easy target. It's an easy win. So I think there are many small things that we can do to improve quite a lot.
Okay, and just when you mentioned the small things that we can do, there's a question here just wondering, is there any best practice guidelines or a manual that has been developed as a result of the catchments work to give to farmers in farmer-friendly language or in user-friendly language, or where can they be accessed if they are available?
Well, there isn't actually, but I find that a very good idea to do something like that. What we have been doing now is actually we've been monitoring quite a long time now baseline conditions, and not until now in this phase of our program we can take this next step further and start testing measures, and that will definitely be able for us to give these guidelines.
Okay, so it's safe to say it's in the pipeline.
Yes.
Stocking density or source pressure and losses to water is related to soil type and rainfall events. Is there a national mapping layer for soil types and pressures that could help with this? Or are you aware of any?
Well, there are soil type maps, obviously, but the luxury we have in our catchment is that we have very detailed information, and we kind of building our understanding from that detail, and then we have to scale down, so to say, well, in information. I don't think that information is available at the national scale, even if there are, of course, maps available. Maybe not of the same resolution, but I think we need to use our information and generalize in other areas. There might be a dominating soil type, and we can use that information when we do draw up any strategies.
Okay, when you mention other areas and you said you have an increase of 65% in your funding, is there an ambition, or are there plans to go to other areas or other regions, or are there soil types that we're missing out on as a result of, I guess, sticking to the same locations for the last 11 years?
Yeah, no, we're not going to other areas, but if we were, I would prioritize. Maybe we don't have organic soils in the picture, for example. So that would obviously be something we will want to know more about. And there would be other areas. You probably saw from our map there that most of the catchments are focused on the coastlines and not so much in the center of the.
Was there a reason for that, Per-Erik?
No, well, actually, they were chosen with a multi-criteria analysis, very robust in way of finding catchments of a certain size and of intense agriculture, and this is what came out of that.
Per-Erik,
Pat, you were going to come in.
A question there in relation to, I suppose, critical source areas that have been identified. Have any measures like riparian zones or sediment traps been investigated within the catchments to alleviate those and get any indication of effectiveness?
Not yet. Again, this is a project that we just started. We have a collaboration with Newcastle University, and where we're going to start, since we've now been, as I mentioned before, monitoring baseline conditions. Now we're taking this step to start testing. So sediment traps is actually one of them, definitely, that we're going to do. We have some really interesting sites where we believe this is going to do a big difference, and we're just being able to test it out and quantify that, and then this is going to be used for models and scale up to whole catchments.
When you mention models, Per-Erik, we have a question here about planning to upscale the outcomes, and are there any plans to digitize or create any additional modeling? I suppose going back to the earlier question, to develop plans on a national basis. Yes,
that's the part we're just about to recruit a new catchment modeler, and that will be one of the tasks.
Okay, so that an advertisement, was it?
Sorry. How can farmers be made aware of critical source areas on their farms? And I suppose arising for that, is there any rules of thumb that you can get or you can give to help people to identify where those critical source areas might be?
Okay, well, first of all, I have a feeling that many farmers have an idea themselves of their land, that they know the areas they're avoiding for being very wet. So they would be naturally associated to wetland where it's poorly drained and maybe close to the rivers, and those areas would be probably the ones that will be coming up on our critical source area maps. They will be low in the topography, and I think for them to be aware of it, I mean, obviously, in the catchment we've been working with, we can, via our advisors, communicate that. But general, on a national level, I think it's the near stream areas that are poorly drained.
Okay.
There's a comment here: soil pH correction could reduce P loss. For example, in the cases of chemical risk control or iron-rich soils, is there a correlation between P loss and soil pH in this chemical control scenario?
I'm sure there is. We haven't looked at that at the catchment scale, although we have had plot trials and found that. But of course, what I've been talking about here has more been results based on the catchment outlet. So that's integrating a 10 square kilometer area, and we haven't seen anything that we can confirm that at that scale. However, at the plot scale, obviously, yes.
You mentioned experimental design at the outset as well, Per-Erik, and that because it's so consistent across the catchments, that's the strength of the overall program. Is there much of a variation in the technology that kind of you started out the catchment study with and what's available today? Could it lead to, like, do you need new technology, or could it kind of enhance your findings?
Yeah, well, technology is developing all the time. I think regarding the phosphorus monitoring, I don't think there's so much more as we speak, but I know a lot of other sensors are being developed, and one thing, I think what's in the pipe in terms of technology is that it's just becoming so much smaller and easy to mobilize. Now we have these big outdoor labs. One discussion is this lab on a chip. So they're really small technologies that can be easily be depleted in multiple places. And that obviously will change things drastically. We will be able to get a lot more insight and a lot more done, of course. But
okay, just on collaboration then, how are you linking up with other organizations? Obviously, there's ACP, there's EPA. You know, I presume from a university point of view, you're linking up with universities as well. But how are you benefiting from collaboration, I guess, is the question here.
This is a big part of the program. We're actually, I think currently we're collaborating with 10 externally funded projects that somehow are linked to the program, either directly or indirectly, and that uses data from the program. So, and that's national projects and international projects. So it's well used, resourced in that way.
Per-Erik, there's a couple of questions coming in, and I'll lump a couple of them into one. Will load management alone achieve the required reduction levels? And I suppose our policy has been predominantly on load management. And the second part of that is, will a one-size-fits-all approach deliver the kind of outcomes that we need?
Yeah, so that's a good question, because load management alone could in some places work, in others not, and that directly then links to that no, there's no one size fits all for this, and the examples I showed you there, for example, with the Bellacanoe catchment, Casadorcal catchment, just neighboring catchments, but one catchment having 3 times higher phosphorus loss than the other despite similar loadings, and attributed to hydrology in that case. And there are other situations that other factors as well that could contribute. So yeah, better load managing could work very well in one catchment and not at all in another one. So we need to understand the landscape better. We need to understand these physical characteristics in each catchment to decide on a good management, efficient management.
Okay, I guess one to wrap up, Pat, we're getting near time there. Yeah. Is there a trend in terms of nutrient loss during the project? I.e., is there an increase or a decrease that you guys are seeing?
We have seen in some catchment there are increases, and some catchment in nitrates and others in phosphorus, and some are entirely steady state. But once the interesting bit there is, for example, one catchment that we've seen a steady increase in nitrate concentration, both groundwater and surface water. In that catchment, there hasn't been an increase in the loadings. So in that catchment, it was more correlated to the weather shift. But we have seen in yet another catchment an increase that was more linked to intensification. So again, there are different reasons for that trend, and other catchments there's been.
So with the weather shift, Per-Erik, what management can take place on those catchments to reduce the impact?
Well, I suppose in that catchment it was a lot. It was the nitrate concentration that was going up, and it's freely drained catchment, arable. So I think winter cover crops would be a good thing. In that particular catchment.
Over to you, Pat.
Okay, listen, thank you very much for that, Per-Erik. I suppose one comment that I would make is we're starting to learn a lot about water quality, but I think and the impacts of various factors, and it's absolutely key knowledge, and it will be key knowledge, I think, for everybody working with farmers over the next number of years to get to grips with. Fortunately, we have a number over the next number of weeks. We have a number of other sessions from the Catchments Programme, so some of your colleagues will be with us over the next number of weeks, which is great. With that, I'd like to thank Per-Erik for his presentation. I'd like to thank Per-Erik for being with us on questions. I'd like to thank our production team, Andy Boland and Yvonne Marr, for organising this on a weekly basis. We're up to 28 at this stage in terms of the series, and the plan is to continue it indefinitely. So with that, I'll say thank you very much for joining us. It's great to have you with us on a weekly basis, and join us again next week for the second of the Catchment talks. So thank you. Bye.
Cheers. Have a nice weekend.
Thanks. Bye.